Okay, so perhaps I will postpone to the end of this lecture what I was going to say this morning about the second situation where check homology works well, because at the end of the second lecture we shall know more things, and we shall be able to understand in a better way that feature. So second lecture is about varieties and bundles. And so the idea is to start from the notion of a complex manifold. So let's assume that we have more or less an idea what a differentiable manifold is. And the idea is that a complex manifold is the same kind of idea, but where instead of considering C-infinity functions, we consider holomorphic functions. And in particular, we shall model our space on open sets in Cn rather than Rn. So the idea is that we have a topological space X, which will have some nice topological properties, which always help a lot in doing geometry on such spaces. Hausdorff, for instance. And then we assume that this is covered. There's some open covering. And we have some homeomorphisms of these open sets with either Cn or perhaps open subsets in Cn. And then we consider the so-called transition functions. Meaning that if we have an intersection which is non-empty, then we have two different ways of realizing this intersection as a subset of Cn, and we want the two different ways to coincide by means of what is called the biholomorphism. So in particular, we require that this map, which is a map from phi beta u beta to phi alpha u alpha, every such map is a biholomorphism. No. Which means that it is holomorphic as a map from an open subset of Cn to another open subset of Cn, bijective with holomorphic inverse. So a very similar definition that we have for differentiable manifolds, but assuming that you are locally modeling over subsets of Cn in such a way that the transition functions are biholomorphisms. The easiest non-trivial, perhaps, example is the projective space. So let me first introduce this notation. So we call C star the non-zero complex numbers, and this, of course, as we were saying this morning, is an abelian group under multiplication. And then we consider, for some value of n, we consider the space as Cn plus 1, deprived of the origin. On this space, we have an action of C star, just by multiplication of all components, so to say, by the same non-zero complex number. And this we shall call Pn, the complex projective space, which of course may be regarded as a space of lines in Cn plus 1. Correct? This is a complex manifold, and we can indeed, of dimension n, of course, and we can indeed consider what is called an atlas, holomorphic atlas, like this. And for instance, if we call W0, Wn the standard coordinates in Cn plus 1, of course, any choice of these parameters will correspond to a point in Pn, unless provided that not all of them are 0. And then these are called the homogeneous coordinates of the corresponding point in Pn. But we can do the following. Suppose we consider we take a hyperplane, we take the complement, so we consider the image of the subset where some fixed homogeneous coordinate is different from 0, and we take its image in Pn, and we call it Ui, and then we get an open cover of Pn. These are n plus 1 open subsets which cover in Pn. And on these we may introduce the so-called affine coordinates, Z1, Zn. So Z1 is W0 over Wi all the way to Zn, which is Wn over Wi. And omitting, of course, Wi in this list as a possible numerator. Okay? And this gives, well, this would be the choice of affine coordinates in the open set I. So perhaps we should also put an index here. And the idea is the collection of these is, well, I'm changing index, the name of the index, but this is what we could call phi in this case. And if you write the transition functions, so we should write something pi times phi times phi j minus 1 of Z1 Zn. This is given by this equation. Actually, we are considering this on Ui, on the intersection between Ui and Uj, and here Zi is different from 0. Because both Wi and Wj are different from 0, so Zi and Zj are different from 0, and Zi in particular is different from 0, and so this is a biholomorphism. Okay, this is holomorphic, and the inverse has the same structure, by the way. If you write it, it's the same object. So this is a biholomorphism. And so, in this way, Pn is a complex manifold. We can add a few comments on this. So we have our projection. And in particular, the sphere S2n plus 1 sits here. We'll look at, of course, identifying C with R2. The sphere, of course, sits here. And then you can restrict. And the restriction of pi, you may show it is surjective. And this implies that Pn is compact. And also, if you take n equal to 1, you just have two open sets. U1, U2, and you just have one transition function, which is something like Z1 is 1 over Z2. And this is a possible atlas for the sphere S2. This means that P1 as a differentiable manifold is S2. So topologically it's a sphere. Of course this is wrong for higher values of n. But this is true for this case. Indeed, this is sometimes called the Riemann sphere. Okay? So this is the first example. Second interesting example that we are going to use is the general linear group of order n. So these are the invertible n times n matrices with coefficients with entries in C. Actually, it's not difficult to realize that this is a closed, is an open subset of Cn square. In this way, it acquires a natural structure of complex manifold. So this is another example. And another interesting example, which I will let you to work out, is a possible generalization of the notion of projective space. So as we were saying, projective n space is a space which parameterizes lines in Cn plus 1. And in the same way, you may think of introducing some space which parameterizes planes, vector subspaces of some dimension in Cn. So, in particular, you can introduce a space, GKN, which, from a point of view, from a set theoretical viewpoint, is the space of K-planes in Cn. And with a little more work, you can prove that this is a complex manifold. Of dimension over the complex numbers, of course, Kn minus K. This is called the Grassmannian of K planes in Cn. And of course, G1n is just another name for Pn minus 1. Okay? From our previous definition. Of course, one could do more examples. By the way, as I was saying, it would be nice to give more examples and solve more exercises. Of course, we have too little time for that, but in my notes, whose link whose URL is on the page of this school, you will find a lot of examples and exercises. Some of them solved, some of them not solved, following more or less the thread I'm following now. So, and now we know what complex manifolds are. Now I would like to start some path which in some way, among other things, will show us that under some conditions to be specified, so we shall consider those complex manifolds which can be embedded into some projective space. And these will have some very special status in the theory due to the fact that, we shall state a general result in this sense, it turns out that they are algebraic, in some sense that we shall specify. Well, algebraic means that they are sets of zeros. I mean, they are the zero set of some set of polynomials. So they may be given by polynomial equations. So in principle, we start from something which is not polynomial at all, and we shall see that under some condition, of course, these will turn out to be algebraic. By no means all complex manifolds are algebraic. So we shall need a strong condition for a complex manifold to admit an embedding into a projective space which will make it into an algebraic variety, as one says. So this goes through the notion of a vector bundle. Particularly at some point, in order to have this embedding theorem, we shall just need the notion of line bundle. But I prefer to start with vector bundles more generally. So we shall start from a complex manifold, X. And then we say what a vector bundle of rank R over X is. So the idea, of course, is that we have what could be called a trivial rank R vector bundle, which is just the product of X times CR. And then we shall consider a situation where X is covered by open set, and on top of it we have some object E in such a way that restricting it to an open set, it will be a product. But on different open sets, this is true only on each of these open sets, not globally. So in other terms, locally we have a way of identifying this E with a product. And again, when we are on a non-void intersection, we shall have two different ways of making this identification, and we want these two ways to be compatible. And this is indeed where the non-trivial structure of a vector bundle comes in. So the idea is that a vector bundle of rank R is another complex manifold E with a surjective map from a holomorphic map from E to X and an open cover, say UI, together with maps psi I, say, from the inverse images of these open sets to UI times CR. So these are these identifications. An open subset, this should be a product. Satisfying some requirements, which are the following. First, let me be a little quick. In some way here, you can write transition functions in the same way, and you require these to be biholomorphisms. The second is a property of a compatibility with, I cited this just for sake of completeness, we need a condition of compatibility between these objects which are called local trivialization and the projection over UI, because actually in principle you have two different ways of projecting over a UI, either directly or first trivializing and then projecting onto the first component. You want this to give the same. So you want commutativity. Oh yeah, sure. Thank you. Thanks a lot. Here too. Thank you. Yeah. So if this is UI, I'm talking about this kind of cylinder over UI. Okay. And then, so we want this to be true. Well, of course, and then notice that up to the point we have no linearity condition. So this is not a vector bundle so far, because we didn't embed any linearity assumption here, and we do that now. And in particular, what happens is that if we, by the first condition, if we take a point in an intersection, and we take the inverse images of that point, which is the fiber, which is called the fiber of the vector bundle on that point, we have two different identifications with the CR. We want this identification to be related by a linear map. What I'm saying is that if I take a point, I have two different images in CR. There is a biolomorphism between them, between the two different identifications with the CR, but nobody tells me it's linear. We want it to be linear. So I will make it shorter by saying that this is linear on the fibers. Okay? So I'm assuming this. So all this structure is a vector bundle. To be honest, is a vector bundle together with its trivialization. Okay? Then a vector bundle is the abstract structure given by this. Well, immediate examples of these are, for instance, you start from some complex manifold which we introduce in explicit way, such as the projective space, and then you can introduce the tangent space to every point, the complex tangent space, I mean, and by considering it as a varying vector space with respect to the point you choose, you get the holomorphic tangent bundle to the projective space, which is an example of this. And more examples will arrive in a moment. Now, as it happens also in differential geometry, I mean the smooth category, if we have a vector bundle with its trivialization, you see that for every point, this is what's written here, we have a linear transformation immediately as a consequence of the third assumption. So this means that if the intersection of two trivializing charts is not empty, we have a map Gij from the intersection. So this is going to be, for every choice of the point here, an invertible linear transformation. So it is an element in GLRC. And this, by birth, is holomorphic. Because everything is holomorphic here. And as usual, you have a cocycle condition, in the sense that if we have a situation where three open sets of the trivialization meet, actually, if you take the fiber over here, we have three different ways of realizing it as a CR. And the compatibility between all these ways give rise to a cocycle condition. This is an equality between these functions computed at some point P in a double intersection, in a triple intersection, sorry. Okay. So we have a transition function. These are what are called actually the transition functions of the bundle. And as usual, one may prove that if you start from a complex manifold, an open cover, and a set of holomorphic maps like this, which satisfy the cocycle condition, you may build a vector bundle which has, with a trivialization, whose transition functions are the given functions. So you can start from the assignment of this transition function. Actually, this has something to do with the check homology. And this will be indeed very useful. And it has something to do with check homology in a proper sense in the case of rank 1. So now we study for a while the specific case of rank 1. In this case, the vector bundles are called line bundles. So to say the standard fiber of such a vector bundle is a C. Okay. And here you see that we are doing the following. Suppose that we are describing a line bundle in this way. So this means that we have an open cover. We have functions from this intersection to C star. Do we already know this object? Yes, we do, because let me call U this open cover. This is exactly a one cochain in the sheaf OX star. Right? For every non-voided double intersection is a non-vanishing holomorphic function. So it is exactly a one cochain here. But actually, it is more than that, because one can prove, well, this by birth is closed under the check differential. Because first, you remember that actually, to say that this is closed under the check differential, Ij, Jk, Ik, I should write something like this. But I'm not writing this because in our case the group structure is multiplicative. And therefore, in order to write down the fact that our cochain is closed under the check differential, I should rather write something like this. And this is exactly the cocycle condition with some changes in the way I have written it. In particular, writing the inverse is equivalent to changing the order of the indices. And I can change the order in which I multiply, because in this case, this is abelian, of course. It's a sheaf of abelian groups. So the order doesn't matter. So this is exactly that condition. And therefore, we have what is called a cocycle, actually. This is not only a one cochain, but it is a one cocycle, which means that it is closed. Okay? And as such, it gives rise to a cohomology class. It's a cohomology class. So this will give me a class in H1 U OX star. Actually, we can say more, because we can show the following. What happens if we have two cocycles whose difference, so to say, is a coboundary? It may happen that I have a situation where I have two different cocycles. So that will be, say, G and G prime. But I shouldn't say the difference because we are in the multiplicative case. So instead of the difference, I should write this. It may happen that this is delta of something. And then we may prove that when this happens, the two corresponding, this happens if and only if the two corresponding line bundles are isomorphic. So this happens if and only if the two cocycles give rise to isomorphic line bundles. Okay, so not only a line bundle corresponds to a cocycle in this cohomology and therefore to a cohomology class, but the relation is one-to-one. So there is a one-to-one correspondence between the classes in this cohomology group and isomorphism classes of line bundles. Okay, I'm cheating a little bit because we have still the open cover around, so I should say one-to-one correspondence between cohomology classes here in this group and line bundles that trivialize on U. Isomorphism classes of line bundles that trivialize on U. Okay, but then I will assume under the carpet that our line band, our open cover is such that this actually computes the cohomology. I didn't put a check here, but if I want to get rid of the open cover, I know I can introduce this space, and I assume that I can choose an open cover in such a way that this cohomology is the same as this. So I forget about the fact that here I'm writing an open cover. Of course, one should prove that this is possible. But again, I don't have time. But this is possible. So I will put this under the carpet. I don't write the open cover anymore. I will write X here, and I'm saying, please be comfortable that there is an open cover which makes the job. So actually, in actual computations, you use the open cover rather. I mean, use the personification of the cohomology group in terms of the open cover. Okay, so at the end of this story, what I want to use now is the fact that there is a one-to-one correspondence between this group and isomorphism classes of line bundles. Of course, I didn't say what an isomorphism of line bundles is, but I'll leave this to your imagination. Okay, so this is a very important thing to do. And now we start putting pieces together because I want to use the long exact sequence in cohomology to study this situation. In particular, I want to use it to associate with a line bundle some cohomology class, which is a kind of topological invariant of the line bundle. And I want to study how far this cohomology class identifies the line bundle. As we shall see, in general, it does not, but we can make up a very precise idea I mean, what really happens, of what really happens. So now we keep in mind that we have this situation. And we go back to our example, actually, of an exact sequence of sheaves. Okay? So we have the sheaf of holomorphic functions on our manifold. We have the sheaf of non-vanishing holomorphic functions, so such the sheaf of those functions which don't have any zero. By the way, this may a nice exercise show that this is indeed a sheaf. This condition of not having zeros is compatible with the sheaf axioms. And here we have the constant sheaf Z regarded as whose sections are regarded as simply holomorphic functions which take integer values. And we said that this is exact in the sense of sheaves. Now, so far we didn't introduce any exotic topology, So X, I assume, is the so-called analytical topology. So in particular, as a complex manifold, it will have transition functions which are B holomorphisms. In particular, this means that they are homeomorphisms. So this is a topological manifold, and it has some topology, and in particular, we may assume this is paracompact. So we assume this, and in our examples, it is. And this means that we may write the long Z sequence of cohomology associated with this. Okay? And let's start from H1 of Z. I know this goes to H1 of OX. This goes to H1 of OX star. This goes to H2, sorry, of Z. This is the first connecting morphism. You remember this morning we saw that when we have a long a short Z sequence, you should go through an intermediate step where you use this to construct some morphisms between complexes, and this will, at the end of the day, produce a long Z sequence in cohomology. So I wrote just a piece of it. Okay. So here inside we have the line bundles. And therefore, we learn that if we start from a line bundle, we can associate with it a cohomology class here. This is an integer cohomology class. In this case, this is just a connecting morphism. This is called the first Chern class. And I can think that an element here is represented by a line bundle. So to any line bundle, I can associate a cohomology class, which is its first Chern class. The first Chern class of L. You can prove the following. So you can prove that this is a topological invariant. So if you have two different line bundles that are really different as holomorphic line bundles, but they are the same as continuous line bundles, they have the same first Chern class. So the theorem is that C1 of L is a topological invariant in this sense. And then at this point we should study what happens here. How far? There are several questions that immediately propose themselves. The first, for instance, is C1 surjective? So it is true that if I give you a cohomology class in H2 of Z, this is the first Chern class of a line bundle. The answer is no, because it's not true that all possible Chern classes of line bundles exhaust this space. In particular, well, perhaps I will not go into this detail. So img is, in principle, this is strictly contained. Here, these are the so-called algebraic classes, but anyway, we don't have time to go to that. This is a name. It's called the Néron-Severi group of X. In general, it's strictly smaller than this. So this is the first question one could raise. And the second is how far, suppose that we have a class which is indeed in this group, in the image of the first Chern class. Does this class determine the line bundle? Well, the answer is definitely, in general, no. And this we may easily see from this. Because if the difference between two line bundles is in the image of this arrow, it will go to 0, because this is an exact sequence. So in particular, an equivalent version of my question is the following. If a line bundle has a 0 first Chern class, is it trivial? Well, trivial means that it's just a product. So it's just x times c. Of course, you can understand that this line bundle has a vanishing first Chern class. Okay, one should prove it, but it's quite reasonable. So the question is, if C1 of L is 0, is the line bundle trivial? And we see that this is not the case because this arrow in general will have a non-trivial image. And if something is in the image of this, it will go to 0. Now, if you think a little bit, so we can study this situation first by showing that actually here we have 0 if X is compact. And this is a result of the fact that we know, I guess, that if we have a holomorphic function on a compact, this is constant. It also has a name, a principle of somebody, but now I don't remember. Also because we Italians share with other nationalities the habit of attributing to Italians as many results as in mathematics, say, or physics, or whatever, as possible. And this, in Italy, it's called the Morera's theorem, but I'm quite sure that it's not called like that out of Italy. I don't remember. It's a maximum principle, yeah.
Famous mathematician.
Sorry?
Famous mathematician, maximum.
Yeah. The result is the following. Well, actually, there is an intermediate thing that we should. Actually, we also need that X is connected. So the first piece of the long exact sequence is this. And then it goes to H1 of Z, the beginning of what I wrote up there. One should, so X connected, one should show this. This is an exercise. We didn't do that, but you could show that the zeroth cohomology group, whenever here we put a sheaf, is the sections over the whole space. And then this is Z. In the same way, this is C, because, so this is the holomorphic functions on the whole space. And if this is compact, not only connected, but also compact, this is C. In the same way, if we consider non-vanishing functions, this will be C star. The upshot of this is that this exact sequence is this one. But this, we know it's exact, ending with 1 here. So here, I can write 1 or 0, and then this means that the long exact sequence splits. There's a first piece with 3 elements, which is exact by itself, and then it starts again with 0, which is this 0. Actually, you also need it connected. Now, I will leave to you again. You see that you are getting an awful lot of things you should meditate upon. So I will leave you the following thing as well. This is general. Just because we have an exact sequence, you see that this injects inside this one. You can take a quotient, and then this quotient will inject into the next term in the exact sequence. Now, so this goes via C1 to H2. Now I will change names to these objects. And in particular, I will write not H2 of Z, but rather the image. And the group I'm erasing in this moment of equivalence classes of line bundles, or isomorphism classes of line bundles, I will call the Picard group. So the second term of that sequence will be the Picard group, where Picard spells in this way. The quotient we start this sequence with, we call pic 0. And here we write the image, the Néron-Severi group. So this will be exact by construction, since I write the image here. So this error is surjective, right? Because I write the image, so it's a surjective by construction. So this map is the third Chern class. And here we see that pic 0, note that it is a group. It's an abelian group because it is the quotient of two abelian groups. And it classifies line bundles having the same first Chern class. So if you fix the third Chern class, you have a whole space of line bundles which are different, non-isomorphic, and correspond to that third Chern class. Actually, just to give a hint to what's going on here, this space has a rich structure. Particular, it's not only a group, it's also a variety, because you can prove that what happens is that under this assumption, this is a finite dimensional vector space. This is a vector space over the complex numbers, to be sure, because OX is not only an abelian group, but I mean, if you consider the holomorphic functions on an open subset, it's a complex vector space. And then this group is a complex vector space. And so this is, if you choose some basis, you can prove that under our assumptions, it is finite dimensional. So it corresponds to, I mean, it's some C to some power, G. G just the dimension of this. And then you can prove that this is a lattice in CG, meaning that it is Z to power 2G with some embedding, non-degenerate embedding into CZ. And if you have an eye for such things, you realize that the quotient is a torus, because it turns out to be something like this. So this is a complex torus of dimension G. Okay, and so we shall have a variety classifying line bundles that have the same first Chern class. Time, please. I forgot. I have the watch up there. Oh my God. So I'm supposed to finish at 4, including questions, right? Okay. Bad news. What about Chern classes of vector bundles? So higher rank situation. Let me spend 5 minutes just to give you a rough idea that we really can do. In the case of vector bundle, we can introduce additional Chern classes. We can do the following. Actually, the first Chern class, we are quite in business anyway because of the following. You remember that a vector bundle may be described by transition functions. Maps, holomorphic maps like this, which satisfy a cocycle condition. Then, of course, at every point, this means that I have a matrix. Of this matrix, I can take the determinant. Correct. Of course, I get an element of a C star. So by composing, I get maps, say, H alpha beta. And of course, H alpha beta are elements in our Check complex, because they will satisfy the cocycle condition, right? Because the cocycle condition, I mean, you take the determinant of the cocycle condition for the G's, you obtain the cocycle condition for the H's. So we get a line bundle. So we started from a vector bundle E, and we get a line bundle, which is called the determinant of E. Just taking, well, this is very rough, of course, but I try to be as quick and efficient as possible. So using transition functions, starting from a vector bundle, you may cook up a line bundle. And then it's very tempting to say that the third Chern class of E is the third Chern class of its determinant. And indeed, this is a good idea. So at least for the third Chern class, we are in business. What to do with, I mean, the idea behind all this is that since we are in a higher rank, we expect to have more Chern classes, not just one. And indeed, there is a class of vector bundles for which it's very easy to introduce higher degree Chern classes. And these are the vector bundles which are direct sums of line bundles. All of R, say. What's the meaning of this? Well, for instance, there's a very easy way of depicting this, again using transition functions. Suppose that we are able to choose a trivialization where at any given point, the transition function at that point, which is a matrix, is diagonal. So this means that we have just elements on the diagonal. And these elements will satisfy the cocycle condition, correct? Because you write the cocycle condition for these G's, and you will get the cocycle conditions for all the elements on the diagonal. This exactly means that E is a direct sum of this. Now I need to do some gymnastics. Because I write a formula, and you may say that the formula makes no sense, but actually the formula makes sense, because I will do the following. So for each one of these line bundles, I have the third Chern class. And now what I do is the following. I take, you know that I can introduce the so-called symmetric elementary functions of, say, R variables. So sigma 0 of these variables is just 1. Sigma 1 is just the sum. Sigma 2 is x1, x2 plus x1, x3. Of course, there are much more refined way of introducing them, but just to be clear, something like this, etc., up to the last, which is just the product. Okay, and I compute the kth symmetric elementary symmetric function on these Chern classes, and I say that this is the kth Chern class. Of course, you immediately tell me, what are you doing? Because I put here inside not numbers, or I mean, these are formal variables, but there must be some meaning in multiplying them, summing and multiplying them. And what I claim is that there is such a meaning, because of course I can sum elements in this group. But my point is that I can also multiply, because in particular, if I consider the direct sum over all values of these cohomology groups, this is a ring, in the sense that I also have a multiplication, which is called the cup product. Actually, the cup product is very easy to understand in the RAM cohomology. Now you tell me that the RAM cohomology has nothing to do with what we are talking about. But actually, you perhaps remember the exercise of S1 of this morning, where I told you that you may check by brute force that the check cohomology of R is the same as the RAM cohomology. This is general, so you may prove that if X is a differential ball manifold, you always have an isomorphism like this. Why I'm saying this? Because in the case of the RAM, it's very easy to define the cup product. Because what's a cohomology, the RAM cohomology class? It's a cohomology class, it's represented by a differential form. Right? A cohomology class is represented by a closed differential form. So a cohomology class is something like this, where omega is a closed differential form. If I have another, it will be something of the same sort. It will be a closed differential form. And then I define the cup product by wedging the representatives. And using the fact that the wedge will be closed as well because of the following Leibniz rule. Okay, you have a Leibniz rule for the exterior differential with a sign given by the degree of omega. But in our case, the omega is 0, the eta is 0, and so the wedge product will be 0. So this is a closed form. It makes sense to take the cohomology class. So you see that in the case when we are dealing with the RAM cohomology, it's very easy to define a ring structure on the direct sum of all cohomology groups. This is just wedge products on the representatives. Now, since we have this isomorphism, we may believe that there is also some multiplicative structure here which is compatible. Okay, then one should check this, but the answer is that yes. There is a compatible, there is some ring structure which under this isomorphism correspond to this cup product. And what I'm saying is that you can do the same with integer coefficients. Actually, you can do the same whenever you can do more than this, but just to keep it simple, easy, you can do that whenever here you have a ring. Then the multiplicative structure is inherited by the cohomology ring of a cohomology group. So you have a cup product, in particular in this space. This cup product is compatible with this grading, meaning that if I consider the cup product of two elements, one of order k and one of order k prime, the result will stay in hk plus k prime. So this is the cup product. Something that you understand very well in the RAM case, again, because if we have a k form and a k prime form, of course, the wedge product is a k plus k prime form. So for the RAM case, we understand this very well, and I claim this is true, generally speaking. And then you see that we have defined something sensible here, and in particular, the kth Chern class, which is the product of k elements in H2, will sit in H2k. correct? So at least for those vector bundles which split, we can define higher Chern classes up to order R, because we have R, we have elementary symmetric functions up to order R. So we have this all the way to CRR. And then usually says that the higher Chern classes are just 0. And the C0 is just defined as 1, regarded as element in H0 of Z. Now you may object that not all vector bundles split, and therefore now there is a somehow delicate point. So not all vector bundles split, this is true, but they almost do it, in the sense that you may use what is called the splitting principle. Actually, this is much more practical than it seems to be, in the sense that it's a very specific construction. Well, at least there is a very specific model of this construction. Anyway, it says the following: you can always find, given our vector bundle E, you can always find another manifold mapping to X, say Y, in such a way that so I can take the bundle and take it back, and this, well, in C infinity category it will split. So if I forget about the holomorphic structure, this will split. So this will be a direct sum of line bundles as C infinity bundles. And then you define the Chern classes as those Chern classes which pulled back to Y will be the Chern classes of the pullback. And actually, this construction will make sense, in the sense that first the Chern classes are in the image of the pullback, and second, the pullback is injective on the cohomology. So this is a good definition. So in particular, this map of manifolds is such that the pullback is injective in cohomology. Anyway, I understand that there is too much which is hidden here. Let me just, so that what I really wanted to do is to define the first Chern class of line bundles in some precise way. And then we may simply agree that there is a way, basically, as one says, by changing base to the bundle, to define higher Chern classes in the case of higher rank bundles. So this is one of the ways of defining Chern classes for vector bundles. It's not the only way, but it's one possible way. Okay. Okay, now, okay, in some sense now I want to start, are there any questions at this point? In some sense, also this lecture could be thought of as divided in three parts. The first was about manifolds, complex manifold, the second about bundles, and now we go to the third part, which is about how using these structures, line bundles in particular, to embed a complex manifold when it is possible into a projective space. It's not the time I have, it's not enough, but it's okay, so I will go on tomorrow. Are there any questions on what we saw so far? Okay, so let's see a few things about, what can we do with a line bundle over a complex manifold. Okay, so X is a complex manifold, and I have a line bundle on it. Suppose now I have a section of this line bundle. By the way, notice the following. Let's spend a few minutes to discuss this fact. I said, let's suppose we have a section. So far, as I'm talking about bundles, we didn't say what a section is, so I define now what a section is. So a section is a map, holomorphic map from X to L. Holomorphic map, such that here we have the projection. When I compose with the projection, I get the identity. By the way, notice that I'm not saying that such sections always exist, because this is what happens. They don't always exist, but let's assume we have one. This is true because we are working in the holomorphic category. Okay? In the smooth category, you can always find sections of course, you always have the zero section, but apart from that, non-trivial sections, it may be possible that our line bundle doesn't have any. So the idea here is that this is X. At every point, you have the fiber over that point, say L of X. And the idea is that when you compute the section at the point X, you get to that fiber. You don't get to another. This behavior is not allowed. So you have this. On the other hand, note the following. Suppose that now, of course, I can do the same if I take an open subset and I consider just section only on the open subset. Okay? So, to U, I can associate all sections of L over U. And I claim that this is a sheaf. This is just a matter of checking that this is a sheaf. In particular, it's a sheaf, for instance, of abelian groups, because it's possible to define a sum. This is a linear object. It's possible to sum two sections. And you can easily prove that it is a sheaf. This sheaf is a kind of twisted version of the sheaf of holomorphic functions. Why? Because we know that as any vector bundle, this line bundle will trivialize. So we know that there is an open cover in such a way that whenever I restrict L to an open set of the open cover, this will be trivial. So this will be U alpha times C. Now you see that if we are on U alpha, or U, say, times C, we consider this as a line bundle over U, and I consider a section S, correct? This, in principle, is a pair of objects. One goes to U, and one goes to C. So I will have something here, say U of P, F of P. But since I want that the composition with the projection is the identity, this U of P is actually P. There is no way out. No? because the composition must give the identity. So you see that what I'm left is just with a holomorphic function. So this means that a line bundle is indeed a sheaf, and when I compute its sections over and trivializing a subset, what I get is the holomorphic functions on U alpha. So I'm not saying that L is the same sheaf as of X, because this is true only locally. It may be very well that I choose an open subset over which L does not trivialize, and therefore this will be false. Indeed, while for this reason it's always true that if I choose U alpha small enough, I do have sections, it may happen that if U is too big, for instance, the whole of X, it may happen that there are no sections at all. Okay? But otherwise, so this terminology section, which for bundles has a different meaning, actually coincides. If I look at a line bundle as a sheaf, the two terminologies coincide. Now, exactly for this reason, you see that if I took a detour after introducing a section of a line bundle, you see that if I take a global section, this at least locally will be given by holomorphic functions. So again, I take a global section, and then I understand that at least locally, the condition S equal to 0 will give hypersurfaces in X. Will give something which will produce something which is given locally by the vanishing of a holomorphic function. This function here. Okay, so this will be actually, of course, I may be in principle having many of them. I will have, now let's assume that X is compact and also connected, which helps. This will be a finite collection of hypersurfaces. It's finite by compactness in X. This is what's called a divisor. Well, to be honest, it's called an effective divisor because it comes from a section. Moreover, we call a point P in X will be a base point of L if, and these two statements are equivalent, all sections of L vanish at P, all associated effective divisors go through P. You see that by the definition, these two statements are equivalent, right? Because these divisors are exactly given by the zeros of a section. So we say that a point is P is a base point of this line bundle if all sections vanish at P, or if all associated effective divisors go through that point. And now we assume that L has no such base points. Assume L has no base points. So as one says, it is base point free. Then I can do the following. Why I'm assuming this? Because now I want to take some global sections, so according to what I said, they are element here. So they are these are a basis of global sections of L. So I said already that the global sections may be identified with the zeroth cohomology group. This is a finite dimensional vector space. It will have some dimension that we call n plus 1. And we take a basis of sections. I want to use this to define a map from X to the projective space Pn. And now we understand why I need this condition, the fact that the line bundle is base point free. Because what I want to do is the following. To the point P, I will associate the sections computed at the point. And I want to look at this as, I'm thinking of this as n Cn plus 1 minus 0 mod C star. And this makes sense only if, 0 must be eliminated. I can't stay with the 0 because then I don't have a good quotient. And for this reason, I need that, I must avoid a situation where all these sections vanish simultaneously. And for this reason, I need this condition for the line bundle to be base point free. If the line bundle satisfies this condition, then this makes sense. I take the class with respect to this quotient, and I get a map. So we realize that a line bundle which has global sections and is base point free defines a map from X to some projective space. Of course, this map may be far, and now what we would like to do is to use this to embed X into Pn. I will say tomorrow what embedding means in a precise sense. But you realize that whatever it means, n must be big enough. And there is no guarantee that this will happen even when L is base point free. This X may have dimension 10, and this may be 1. Okay, so we need to do something. Anyway, for the moment, what we are saying is that a line bundle with this property will define a map to projective space, and tomorrow we shall see under which conditions this will be an embedding. And then if we succeed in having an embedding, this means that X will have become a subvariety of Pn. And then we use a very strong result, which I will recall tomorrow again, which is Chow's lemma, which says that any analytical subvariety of Pn is actually algebraic. So it's given by the vanishing of a set of homogeneous polynomials. And so those varieties, those complex manifolds, which are able to carry on them line bundles for which phi L is an embedding, become a specific class of manifold that we shall call algebraic varieties, because they can be embedded as algebraic subvariety of Pn. Okay, so this we'll do tomorrow, otherwise I'm running too much. Okay, questions? It's not good when there are no questions, because it means that I lost contact with the audience. Thank you. Yeah.
Instead of homomorphic line bundles, considering like a topological bundle, is the shared homomorphism like isomorphism?
Yes. For line bundle, topological line bundle, C1 identifies the line bundle. Correct.
And if you are like in a smooth category,
2.
It happens in the homomorphic category. It doesn't happen.
Yes, and that happens because if you look at that sequence we used, so that was C1 is here. And on this side we have H1 of OX. And here I never wrote it, but we have H2 of OX. Correct? And in those other categories, these two groups are zero. Basically because both continuous functions on a paracompact topological space and infinity functions on a differentiable manifold are the mid partitions of unity. And that kills the cohomology in positive degree, particular degree 1 and 2. And therefore, in that case, these are not here. And then, if you think what an exact sequence is, when you have 0 here and here, it means that this is an isomorphism. So the answer is yes. More questions?
Any more questions?
So for the splitting principle that you wrote, this map F, does it have to have special properties? You said you didn't specify what.
Yeah. I could answer in two ways. First, you can prove that you always find a map like that, such that first it is injective in cohomology, and second its image contains the Chern classes of the vector bundle. Otherwise, what I wrote makes no sense. So I wrote that the pullback. Well, this is the Chern classes of the pullback. So first we need that this makes sense. And second, we need that this identifies the Chern classes. So we need this to be injected in cohomology. And you prove that this can always be done. And by the way, it can be done also in a canonical way. So if you start from a vector bundle, what you can do is that you can projectivize it. So the fibers are compact vector spaces after all. And so you can take, so this is a very rough way of stating what happens, but anyway, you take the projective, as associated projective space for every fiber. You remove the zero section, whatever. So you get a bundle in projective spaces. On top of this bundle, there's a canonical line bundle, which has this funny name. And then what you do is that you have an exact sequence like this. And here you have a quotient. Suppose that the rank of E is 2. Then this is a line bundle, and the quotient is a line bundle as well. And then, well, either in the holomorphic category you are happy like this, because the Chern classes behave as if this was the direct sum of these two. There is no need to split the sequence. Or you go to the infinity category where all sequences of vector bundle actually split, and then this splits as a sum of two line bundles. And then this is, in that case, this is the splitting, this is Y in that case, for rank 2. Otherwise you iterate. Because if the rank is not 2, this is a line bundle, this will have some rank, and you iterate the construction. You take the projectivization of Q, this is something which sits above this, and you go up. And you know that after r minus 1 steps, you get something which does the job. For a very good, not for complex manifold, but it's absolutely enough, because for defining Chern classes, we may forget about the holomorphic structure. We can just consider bundles. Bundle is the book by Bott and Tu, which is called Differential Forms in Algebraic Topology. And well, the technique was invented, as far as I know, I believe, was invented by Borel and Grothendieck, and there's a paper by them. This is the algebraic technique.